So we've gotten pretty good at taking derivatives, but now we want to be good at understanding derivatives. And in particular, suppose we know information about our derivatives, what can we conclude about our function? And so we're going to look at, in particular, the first derivative and say, hey, what information can we gain by understanding the first derivative? So let's get into it. Now, the basic thing we want to talk about is what's called increasing and decreasing. Now, it's kind of intuitive when we talk about something being increasing. So we have an orientation. So we often go from left to right. So when we talk about saying a function is increasing, it means that as we move from left to right, the value is going up. So I'm moving up from left to right. To say a function is decreasing, as I go from left to right, the value of the function goes down. So I have a downward movement. So the way we can define this, of course, is we always have to add a little bit of confusing math terminology, don't we? We say, look, if I compare the function at 2 points, c and d, where c comes before d. So here's my value c, here's my value d. And I want to say, well, which one is bigger? So if it's always the case that the one over here is larger, well, what does that mean? Well, that means I'm increasing. But if it's the case that the one over here, the first point at c is larger, that means I'm decreasing. All right? So that's the idea. So if c is less than d, f of c less than f of d, that means I went up. If c is before d, but f of c is greater than f of d, I move down. All right, so not so hard to imagine, but what does this have to do with derivatives? Well, we know that derivatives give us information locally about a function. So we know, for example, if our derivative is positive, it means that locally our function looks like a tangent line, which is positive. So it has a slightly upward slope. Aha! What does that tell us? Well, so locally it looks like a line which is increasing. See, we know when lines are increasing. A line increasing means positive slope. A line decreasing means negative slope. And therefore, we say, aha, if our derivative is positive, nearby we look like a line with positive slope, which means that nearby we're increasing. Now, of course, there's always the catch. What does near mean? Well, sufficiently near. All right. On the other hand, if the derivative is negative, locally we look like a line with negative slope, and therefore nearby, again, that word near, we're decreasing. So this gives us a way to, in some sense, test locally around a particular point. Can I say whether my function is increasing or decreasing? And of course, if we know the derivative at all points, we can gain a lot of information. So we have the following. If our function is differentiable, of course, remember that just means we can take a derivative. So if it's differential between a and b, and the derivative is always positive between a and b, then we say it's increasing between a and b. On the other hand, if the derivative is always negative between a and b, we say it's decreasing from a to b. Now you might notice there's kind of a small subtle catch here, and of course, as with all small subtle catches, it stands out. Notice how we have these inequalities here. You see, we're talking about a less than x less than b, the derivative being positive, but for increasing, we include the endpoints. Now you might want to say, wait, why? Well, there's a small thing that we have to understand. So a lot of people like to think of, oh, increasing, decreasing is a derivative property. And that's not the case. The increasing, decreasing has to do with the behavior of the function and how the function varies. And it doesn't have to do with derivatives. What is true is that derivatives give us information about increasing, decreasing. So what's the case? Well, let's just do a really easy example. Suppose we look at a simple function, let's say f of x, which is x cubed, right? Okay, well, if you look at that function, you can say, where is it that the derivative is positive? Well, you can say it's positive because we know what the derivative f prime of x is 3x squared. Well, this is positive as long as x is not 0. So, what does that tell us? Well, that says it's certainly increasing everywhere, but wait, what about 0? Well, you see, increasing is always about comparisons. I'm comparing one value of the function to another value of the function. So either it goes up or down, or it goes down or up. So I can't talk about I'm increasing at a point. What I can talk about is I'm increasing near a point, because that says, okay, I can make comparisons because I have multiple things to draw from. So the point here is that this function is always increasing in the following sense. No matter which 2 points you pick, if I pick a point here and if I pick 0, well, the point here is below there, so it's increasing. If I pick 0 and I pick here, then again, I'm increasing. So no matter which 2 pairs of points I pick, it's always the case that the one on the further to the left is going to have a lower output than the one further to the right. So that's the case where, okay, the derivative is 0, and it makes sense to include 0 as to where it increases. So this increases everywhere. So that's why we include the endpoints, because it's always about, well, what happens at the endpoint? So oftentimes those are places where the derivative might be 0. There's another possibility, of course, which is you could have a place where the derivative is undefined. Now, you can do this pretty simply with a piecewise function. You could say f of x is, for instance, x if we're below 0, and 2x if we're above 0. And if you sketch this function, you're going to get something very similar happening. Namely, what you'll see is we have a slope of 1, and then we get a slope of 2. So we're a shallow slope, and then we're a steep slope. All right. Now, where are we increasing? Well, again, we're increasing everywhere, because no matter where you make comparisons, we're always going up. But the derivative, it's not defined at 0, because it's a place where there's a, so, all right. So anyways, that was a long side note to say that's why think about the endpoints. Endpoints can make a difference. Now you might think, well, okay, that all makes sense and it's reasonable. We've had some pretty long discussions among faculty about whether or not to include endpoints. So this is my take. You should include endpoints. All right, so how do we put this together? Because our goal is, let's try to understand when a function is increasing and decreasing. In general, overall, where is it going up? Where is it going down? So we say, okay, if we know where it's positive and where it's negative, then we're good to go. So the question is, well, where can I switch? Where can I switch from going to positive to going negative? Now, if you think about the intermediate value theorem, something we talked about before, it says, well, suppose I'm negative here and I'm positive here. Well, what had to happen in between? Well, 2 things could have happened. One, you could have crossed through 0. All right. And the other thing that could have happened was you had a jump. There was a discontinuity. So if you're continuous, you have to cross through 0. And if you're not continuous, there's a jump. Now, where could it be a case where our derivative is not continuous? That could be where the derivative is undefined, like there's a missing gap. So we're going to be focusing on saying, okay, if we focus on where are the zeros, where are the undefined points, well, what we're getting into are points which are critical to our understanding. All right, good. Now, one more phrase you may run across. There's something called monotonic. Now, the word mono, you can think of it as meaning like one, like a monocle. So like we see those old-timey Monopoly player having. Okay, the word tonic is a type of drink. So this is something that requires one drink to understand, right? No, in this case, mono here does refer to one, and tonic is more of a behavior or form, and therefore it has one behavior. So when we say something is monotonic, what we mean is it's always going in one way. So it's always increasing or it's always decreasing. So if you hear us use the phrase, something is monotonic, it just means always either going up or always going down. All right, so how do we actually do this? So what's the process? So we want to find where our function is increasing and decreasing. So it's a pretty simple process. We now have a pretty good idea of saying, well, we know to look where a derivative is positive or negative, and so the first thing we ask is, where can it change? So that's step one. Find where the derivative is 0 or undefined. That's where we can do our switch from positive to negative. So in other words, we're going to make a list of our critical points. Now, what do we do with this? Well, what we do is we imagine we have our number line. So here's our number line. And then we mark where our critical points are. So they might be at some various places. You might have some which are close together, and you might have some which are far apart. Doesn't matter. I mean, it just depends on the function. All right. Now, we're not done yet. What we've done is we said, hey, what's happened here is we've now split our line up into a series of segments. Now, here's the key idea. Each one of these segments here is going to have a same behavior. In other words, each one is monotonic in that section because it's always going to be either going up or always going to be going down. So our goal is to say, well, what's the behavior in each section? Well, because it's always either going up or always going down, I just need to figure out what happens at one point. And because we know we've already identified the critical points, we know that the derivative will not be 0 anywhere that's not been marked. So anywhere on the interior of these little intervals, the derivative is not 0. So how do we figure this out? Well, what we do is we come along and we pick a value. Now, you might say, which value do we pick? So we pick and here's a useful thing to keep in mind, convenient value for each interval. All right? So why do I use the word convenient? Well, there's infinitely many numbers to pick for any interval. You want to pick one that's easy to determine. And so that's your goal, is just figure out what's easy to determine. And by the way, on a side note, you'll see that oftentimes if you can express your derivative as a product of things, in other words, we're able to factor it, it's going to be a lot easier to figure out what's going on. All right, so pick a convenient value, and you have to do it for each interval. Now, the thing is, you cannot pick any of our critical points, so you have to pick. Sometimes they might be close, sometimes they might be far away. You just, pick one for each one. Now, what happens? Well, you pick a convenient value, you plug it into, not the function, into the derivative, because our goal is to understand what's happening around those points. So, what do we get? Well, we'll get things such as, maybe we'll see, we'll just make this up. We'll say the derivative at this point is positive. And notice, I don't even say derivative at the point, I just say the derivative is positive. Because once I know it's positive at a single point, it's positive everywhere inside. All right, well, now what? I repeat. Maybe it's the case that the derivative is, again, positive. And then over here, maybe the derivative is negative. And then it goes back to being positive. So you have some sequence. You have to test every interval. It's not just enough to say, okay, I've tested one interval, then I'm going to always flip sign, blah, blah. No. It's possible that you might not change sign at a critical point. Now, how do we know it's possible? Because we did it. In fact, that was one of the examples we did, was x cubed. Because we saw x equals 0, that's a critical point. We didn't change sign as we moved from below 0 to above 0. Okay. So, what does this allow us to conclude? Well, what we have is wherever the derivative is positive, on those intervals, we're going up. So we can see we're going up in certain places. And wherever the derivative is negative, in those places, we're going down. And now, we can put it all together. So we can see where our derivative is positive, we can see where our derivative is negative, and we see where things are going up and going down. Now, it's possible we can combine things together. So you see here that we have two consecutive positive intervals. Well, if our function is defined at this point, so it's continuous, it's possible that there's a discontinuity, in which case, forget it, you can't do anything. But if it's continuous at this point, it is possible that these might be merged, but it needs continuity. So keep that in mind. So if you're looking for the full intervals, then there you go. All right, so that's our process. So sorry, I went kind of slow there. So it's a lot simpler than it sounds. 1, find your critical points and use that to chop up your line. 2, now for the chopped up line, for each interval, plug in one point into the derivative and determine the sign. And keep in mind, we only care about the sign. Whether or not it's, positive 100 or positive 2 or positive 0.1, we don't care. We don't care about the magnitude of the number. We care about the sign of the number. Okay, so where are we? We cut up our line. We plugged in a point to determine the sign, which says we have now an understanding of what happens on each interval. And so the last thing is pretty much put it all together and give the answers. It's actually pretty straightforward. And once we do some practice, it'll become pretty natural. Now, there is one other thing we can do using the first derivative and using the fact that we know how things are increasing and decreasing. It's called the first derivative test. Now, part of the name gives away what's happening. You'll see that it's called the first derivative test, which means we're going to use the first derivative. It's not just the first test we've done that came up with the first derivative, but rather it really comes up with the first derivative as being a tool. It's about classifying critical points. So we have critical points. We want to say, well, what are they? Remember that we said something a while back. We said in a former session that when we're talking about critical points, that a local max and a local min can only occur at critical points. So the question is, I have a critical point. How do I know if it's a max or a min? So that gets into classification. Am I a max or am I a min? And how can I know? Well, we think about what must be true. We say, okay, if I have a critical point, I'm trying to understand the behavior nearby. So for example, a max says I should be larger than things nearby. So we say, okay, well, I can look and say what's happening on either side of my critical point. So if here's my critical point, I can say what's happening to the left of my critical point, what's the behavior, what's happening to the right of my critical point, what's the behavior, and then put it all together. So what do we have? Well, there's a couple of possibilities. So here's our critical point at our point C. And then we say, well, let's look on what's happening to the derivative on either side. If the derivative is positive before and negative after, what does that mean? It says positive says we're going up. So we're moving up. Negative says we're going down. So we go up and then down. So oftentimes, we draw in certain this kind of format. I just like to just say, okay, going up, going down, and then I can see, aha, boom, boom. That's got to be a local max. So looking on either side, I can understand the behavior. If I'm negative before C, I go down. If I'm positive after C, I go up. So it probably looks something like this. It can have more exotic behavior, keep in mind. But for now, let's just say it looks vaguely like that. If I'm going up, then up, well, then I'm neither a max or a min. So that's be careful. Critical points do not have to be a max or a min. They might be neither. They're sort of like a sort of a plateau. So I'm like the x cubed function had this behavior where we came up like, then we went back up again. Or we could be going down and down. And again, that's not a max or a min. And it's easy to come up with examples of functions which have all these. We already mentioned x cubed. This could be negative x cubed. This could be x squared for a local min, negative x squared for a local max. Like I said, the pictures can be slightly different. You can, for example, you can look at this function. If you have f of x equals x to the 2/3, well, what does that look like? If you sketch it, it looks like that. So it comes in really sharply at 0. And the claim is, hey, that's a local min. Well, you can check. Well, what's the derivative? F prime of x. So that's 2/3 x to the minus 1/3. And now, if you plug in a positive value when you plug it and get the negative 1/3, that's going to be a positive output. By the way, if you're not comfortable with that, you can write this as 2, 3, the cubed root of x, if you want to write it in a more algebra-friendly way. And now the cubed root of a positive number is positive, so what you see here is that it's a critical point at 0, because at 0 you'd have 0 to a negative exponent, which means you're blowing up. So 0 is critical. And then when you plug in something positive, which is to the right of 0, we say, aha, the derivative is positive. Plug in a negative number when you take the cube root is negative. It's negative to the left. So I'm going down, then up, and so I have that shape. So again, you might look a little bit different. You just don't know. We don't have enough context. But our real goal here is to say, how do you classify? So define critical points, take your derivative, set it equal to 0, find where it's undefined, there's your critical points. To classify, just say, hey, let's look at what happens on either side. In fact, really, you can do a lot of work by coming back and looking at like a number line here. So each one of these critical points we could classify. For instance, here the derivative is positive, then positive. So that says we're going up, then up. It's neither max or min. All right, how about here? We're going up because derivative is positive, derivative is negative. Up, down, that's got to be a max. Over here, we have the derivative is negative, then derivative is positive. So we're going down, then up, down, up. We're at a min. So in the process of figuring out where the function is increasing, decreasing, you automatically figure out where are your local maxes and local mins. So it's kind of a nice process. Very similar process, and you'll see some of the same steps done. So, all right, good. Now, you might say, well, first derivative test, is there a second derivative test? Good question, and a great topic for another session. But for now, we should go and do some practice.